multiplying decimals. Of course, we're going to want to start with a review, just to be sure that you remember this wonderful process of multiplication by hand. Again, what you need to do is line up the two numbers you're going to multiply, then starting with the rightmost number, usually on the bottom, you would multiply the 5,712 first by 4, and line up the result, the product, underneath the 4. Then you would repeat the same thing with the 3, line up the product under the 3, and really remember that means that the 3 actually represents something with a value of 30, so that in a sense, next to the 6 in the product, if we wanted to do it fully with all the zeros, we could put a 0 after that 6 to the right of the 6, because the 3 in the 6,534 represents 30. Then we do the same thing with the 5 term and line that up under the 5, remembering it really represents a 500, and do the same thing underneath the 6 term, realizing that has 3 zeros after it, it's a 6,000. Then when we get each of those partial products lined up correctly, we add all of that up, again, just as you would do a regular addition, starting on the right and working your way left as we do it. And I'm not going to go through this addition with you. I'm sure that you've had plenty of practice at this time, but that's the final result with doing large multiplications, multiplications of large numbers manually. Now let's look at multiplying decimals, and in order to do this, I'm going, as I have before, to sneak up on something. I'm going to start with basic principles we already know and have worked with, in other words, fractions, and then I'm going to use what we've learned with fractions and apply that to decimals. Let's look now at what happens when we multiply 0.5 by 0.9. We can represent that multiplication as fractions. 0.5 is equivalent to 5/10. 0.9 is equivalent to 9/10. Now we can use fraction multiplication, and which we remember, I hope. Remember, we need to multiply the numerators together and the denominators together to get a result of 45/100ths. Now that we have that, we can reinterpret the 45/100ths as a decimal, and we see it's 0.045. One thing we could do to check ourselves is ask, is that a reasonable thing? And remember that 0.5 is 5/10, which is equivalent to 1/2. And what's 1/2 of 0.9? Half of 9 is 4.5, so roughly half of that is 0.45, and so it looks like our answer is reasonable. What we've done in this case, remember, is used the idea of fractions, which we've already discussed, to see what we would do to multiply decimals. Keep an eye on the number of decimal places we start with each of the two factors, and then look at the number of decimal places in the product. Let's do another example, again using fractions to get at the decimal result and looking for any kind of systematic things that happen. 0.4 is equivalent to 4/10. 0.06 is equivalent to 6/100ths. Let's multiply 4 times 6 is 24. 10 times 100 is 1,000, so we get 24/1000ths. Interpreting that as a decimal, it's 0.024. Just so that you will see by comparison, I'm going to do another problem on this same slide. Let's try 0.07 times the quantity, 0.008. Notice that what I'm doing is representing smaller and smaller fractions, or another way of thinking about it is fractions or decimals with larger and larger numbers of decimal points. Again, I'm going to convert this to fractional, its fractional equivalent. I'm going to multiply it, and in this case I have 56 hundred thousandths, and I represent that as a decimal. In each of these cases, notice that in 0.4 and 0.06, I had one decimal place in the 0.4, two decimal places in the 0.06. Notice how many decimal places are in the product. In the case under the line, I have 0.07, that's two decimal places, three decimal places in the 0.008. Look at the result. Look at the product. How many decimal places do I have there? Let's take a look at what the progression was in these three examples. We start to notice that there's a pattern here. First, the pattern is 5 times 9. If I just look at that as a multiplication of numbers, I get 45. 4 times 6. If I just multiplied those as whole numbers, I would get 24. 7 times 8 is 56. The first thing I notice in this pattern is that the numbers, if I just take them as whole numbers, are the same as decimal multiplication. I notice something else that's quite important. When I start looking at the number of decimal places in each factor and then the decimal places in the product, what I see is that I can count the decimal places in the factors, and that's equivalent to the decimal places in the product. For example, there's one decimal place in the 5, one in the 9, and I see that there are two decimal places in the product, 0.45. I count up the number of decimal places in the 0.4 and 0.06. That gives me a 3. If I add those places, I notice there are 3 places in the product. And similarly, 2 and 3 decimal places respectively in those two factors, and the product has 5 decimal places. 2 plus 3 is 5. Therefore, I would say that I seem to, in these examples at least, have established a pattern that would be useful. Let's look at yet another case, and again we're going to convert these to the fractional equivalents and work on them that way to see what happens. 5.6 times 3.8. I can represent that as 5 and 6/10 and 3 and 8/10. In order to do this multiplication, the next thing I need to do is convert these to improper fractions. Reviewing that, to convert 5 and 6/10 to an improper fraction, I would multiply the 5 times the 10 in the denominator, add 6 to that. That would be the numerator of the first fraction over 10. If I multiplied 3 times 10 plus 8, that would be on the top of the second fraction. There it is expressed. So 5 times 10 is 50 plus 6 is 56. 3 times 10 is 30 plus 8 is 38. Now I do the multiplication. Again, in this case, I could do it longhand just as we saw, use my calculator, and I see I get 21/28/100, 2,128/100. Now if I express this as a mixed number, I would get 21/28/100. Again, what I would do to get this result is to divide 21/28 by 100, and then the remainder is the 28, which I put over 100. And then I express this as a decimal equivalent, and I see it's 21.28. I notice something. Again, the rule seems to hold. I had one decimal place in the 5.6. I had another 1 decimal place in the 3.8, and my result had 2 decimal places, 21.28. So it looks like this addition of decimal places in the factors to get the decimal place in the product is a valid rule. Every example I've chosen seems to work. Now, of course, this doesn't really, honest to God, establish it mathematically as a real mathematician would want to do it, but good enough for rock and roll. We're seeing a pattern, and we know that no matter what example we take, this pattern always seems to work. Let's look at now a more direct way of doing this, changing decimals into fractions, then fractions back into decimals, is annoying. We'll use the previous example and try to do it in a more straightforward way, just like regular multiplication. 5.6 times 8. Let's just say we have 56 times 8, and we multiply that. Then, treating it as if it were just whole number multiplication, we'll multiply 3 times the 56 and get that. Now we add those together, and then understanding that since the 5.6 is to 1 decimal place and the 3.8 is to 1 decimal place, then we can look at our result as a whole number and know automatically 1 plus 1 is equal to 2, so that we can count 2 over from the right and know that our final result, our product, is 21.28. By estimating, we can see that's close. 5.6 is close to 6 if I were to round it, and 3.8 is close to 4. 6 times 4 is 24, so that result looks in the right ballpark, and we have that additional assurance that our answer is correct. Let's summarize what we've learned here. It follows the same pattern. We multiply as if we were dealing only with integers. Then the number of decimal places in the product is equal to the sum. You count them up. The sum of the decimal places in each of the factors. Let's look at something really complicated. 35.412 multiplied by 14.345. I'm just going to zip through this multiplication. It's a monster, but those are 2 huge numbers. Now I multiply that, and I see that in the factors there is a total of 6 decimal places. So I count over 6 places from the right, and my final result is 507.985140. That's all there is to decimal multiplication. You multiply as if it were a whole number, then you count the number of decimal places. Let's look at another example. Let's look at a really interesting little example. 0.0136 times 0.00649. Let's do this according to the rules, and we'll see something interesting is going to happen, and I'll show you what to do about it. Let's set the multiplication up just as we would a normal multiplication, and we're going to act as if we're multiplying 136 by 649, and then we'll take care of the decimal places later. When we perform this multiplication, exactly as you would a regular multiplication, we find out we're left with 88,264. But we need to account for all of those decimal places because we know that our result is going to be a lot less than 1 because both of the numbers we're multiplying, both of our factors, are way less than 1. Let's look at the places. First, I'm going to throw a bunch of zeros in there. I'll show you why. We have 4 decimal places in that first factor and 5 decimal places in the second factor. That totals 9 places. I'm going to need to count over 9 from the right to be able to find where to put the decimal place. The problem is my product only has 5 digits. I'm going to need to add more digits in order to count over 9, so I throw those extra digits in, then I count over 1, 2, 3, 4, 5, 6, 7, 8, 9, and I see that I needed those extra digits in order to put the decimal point in the right place. When you have one small number times another small number, when you multiply them with decimals, of course you get an even smaller number. And in this case, we had to add more zeros to the left in order to account for how many places we had to count over. So if you start to count in one of your products and you find you're running out of places, you just need to fill in with zeros until you get it right. Let's look at another fast problem using multiplication of decimals. After he retires, John will receive 0.63 or 63 hundredths of his regular salary of $3,456.45. How much will he get each month after retirement? There's the information we're given. Here's what we're asked. Let's summarize that. We're given he gets 0.63 of his salary after retirement, and there's the salary. We're asked what is the monthly stipend, and we can think about there is his whole salary in terms of a diagram, and 0.63 is a bit more than half. We know that the stipend is going to be the salary times the factor. Whenever you hear an of in a case like this, 0.63 of something, that indicates a multiplication. Let's do that multiplication again as we normally would, and we get that. Now we see that since there are 2 places for cents and then 2 places in that factor, we have a total of 4 decimal places, so we count over 4 as we did before and put the decimal place there. Our final result is that the stipend is $2,177.56 and some odd cents. Now, since we're only dealing with cents, let's round that off to just 56 cents. And typically, if you're dealing with money and you do a multiplication like this, you can only report to the nearest cent, so you always round off to the 100th place. Let's look at decimals with exponents now. And for example, suppose we have 0.3 cubed. What should we do with that? We need to remember that what cubed means. It means that thing by itself times itself 3 times. Now we need to account for the number of decimal places. If I multiply 0.3 by 0.3, each of those has 1 place, I get 0.09. Remember, 1 place plus 1 place is 2 places. Now if I take the 0.09 and multiply that by 0.3, I have something with 2 decimal places times something with 1 decimal place. 2 plus 1, amazingly enough, is 3, and I need to count over 3 places. If I just multiply 9 times 3, I get 27. I need to put that other 0 in front. I find out now my result is to 3 decimal places. Let's look at another example of this to see if we can get some kind of a rule. If I have 3.28 squared, that's 3.28 times itself. When I do that, I notice that my final result now has 4 decimal places. Notice that I have a square as the exponent and 2 decimal places. Think about 2 times 2. Let's see now if we can find the rule. 0.3 cubed gives me 3 decimal places. 0.28 squared gives me 4 decimal places. What does that suggest? If I talk about a rule, I can take the number of decimal places in the number times the exponent is equal to the number of decimal places in the result. We saw that happen. So if I have something, whatever number 0.1 cubed, 1 times 3 is going to give me 3 decimal places in the result. Let's investigate the rule with 0.04 to the 4th power. First thing we need to do is find out what 4 to the 4th power is. I can do this and see that it's 256. Now I have to worry about the number of decimal places. I have 2 decimal places to the 4th power. 2 times 4, according to our rule, is going to be 8. Our result needs to have something to 8 decimal places. I can write it like this. There's the 256. Let me throw a whole bunch of zeros in there. I'm not sure where that's going to wind up until I start counting. Then I count back from the right-hand edge 8, and I put the decimal place where it belongs, and I'm done. So doing a decimal raised to an exponent like this is a two-step problem. First, you do the math as if you were doing it on integers, and then you figure out where the decimal point goes. Let's use this on something called scientific notation. Often you might have seen this in your science books. You'll see numbers like 1.234 times 10 to the 5th power. Typically, with scientific notation, it will start with a decimal number between 1 and 10 times 10 raised to some power. Why is that useful? Why should we bother with this? Let's take some really big numbers. For example, there's the distance across the Milky Way galaxy where we live. Seeing all of those zeros can be confusing if you're trying to sort that out. We can rewrite this way with scientific notation, and that will take into account all of those zeros and make it easier for us just to look at that and understand what's going on. Oh, 10 to the 17th power, that's a lot of zeros. It's more compact, as you can see, to write very, very large numbers or small numbers in scientific notation. Let's see how we would change a number written out into scientific notation. Let's take the distance from the Earth to the Sun, 93 million miles, and change that to scientific notation. The first thing I would do is say, let's look at that and see that it's 9,300,000 times 10. Then I can go 930,000 times 100, or 10 squared, 93,000 times 1,000, and so forth, continuing down this chain of logic until I get 9.3 times something. In other words, I keep moving the decimal point, moving the 0 over 1 until I get a number between 0 and 10, and then I write that down. So the equivalent of 93 million miles is 9.3 times 10 to the 7th miles. Let's look at another example. What's the distance from Earth to Alpha Centauri? It's a lot of kilometers. Let's change that. We start at the right and start counting off to the left to see what we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, and finally we wound the decimal point where we want it, 4.12. That's a number between 1 and 10. Now we know also, since we've counted 10 to the right, we can now write this as 4.12 times 10 to the 10th kilometers. To change something to scientific notation, you just start counting over right to left until you put the decimal point at a place where the number is going to be between 1 and 10, and then raise 10 to the power of however much you've counted over. Let's now look and see how we would use decimals with polynomials. Let's look at the case where we multiply a couple of monomials first. As you'd suspect, we do this exactly the way we would with just integers, except now, because the coefficients have a decimal in them, we need to do a decimal multiplication to work it out. And we could do that as a secondary problem and follow exactly the same rules we have before. 7.4 times 8.3 is 61.42. Then we do the rest of the monomial multiplication exactly as we've done it in the past. The only difference is the coefficients are now slightly more complicated to multiply. What about the case where we have polynomials with coefficients or terms that are decimals? Again, it works exactly the same way. We use the FOIL method. First, outer, inner, and last. Except in this case, you see, in addition to having to worry about the multiplying the unknowns or the variables, we need to do 4 separate decimal multiplications in order to get our final result. Otherwise, the procedures are exactly the same. We do these 4 multiplications following the usual rules that we've established before. Then we put our final result together and do exactly as we would. Then, of course, we want to combine, and this is going to call for some addition of decimals. We combine like terms, and we're